So we'll continue with the exercises. So now the goal that we have are two. So we're going to first see how we can use the MOA from the command line, and then also we'd like to see how we can improve the accuracy of our method. So we'll try to see how to use these trees and ensembles that we have seen, how we can use it in MOA, how we can get a better accuracy. So this is going to be the goal. So we'll go here to see how we should use the command line. So the idea is that we need only basically from the command line, we're going to use it, we're going to call the MOA jar using the Java command, and then we are going to use this moa.doTask. This is the one that is going to to tell that we want to perform this task, and the task is going to be the same that we are using in the graphical user interface. So in this case, if we look at the graphical user interface, we see that here basically what we have is we have the command line of the task that we want to perform. So the only thing that we need to do is we need to double click and then do copy configuration to clipboard, and then we can reuse this to run the experiment. Okay, so yeah, this is very easy. So first we are going to see how we can learn and evaluate models. So imagine that there is need to store the model that we are learning, and we need to serialize it. So the thing is that we have one specific task that is called learn model. That what it's going to do is that it's going to learn a model, it's going to train the model, but without evaluating it. So it's going to, we need to specify what is the classifier that we're going to use. In this case, it's the holding tree. What is the data stream that we're going to use, how many instances, and then where we want to store the model. Okay, so let's try to do this. So we take this command line, we copy, and then from the command line we can paste it, and then we can run it. So basically now what we are doing is that we are running this task, is learning the model, and is going to store the model in a file. So you see the output of this task is this tree. So this is the structure of the tree, and this is what we have stored now in the file. Okay, so now the next thing is that we want to reuse this classifier that we have stored in the file. So basically what we're going to do is that we're going to use this evaluate model, and we're going to say that the model comes from this file. Okay, and again now we need to specify what is the data that we're going to use to train, and how many instances we're going to use to train. Okay, so we do this, we copy and we paste, and now we see we are evaluating using this classifier that we stored. Okay, and now we see the result. Classification accuracy is 84% and kappa statistic is 76%. Okay, so this is what we've got here. Again, now, can we do that together? Yes, it's very easy. Instead of when we use evaluate model using the file, we're going to use this task. Okay, so instead of having the file, we're going to put this task that generated the file. Okay, and then we doing only one task. We are performing the two tasks at the same time. So this is nice to show that MOA is very flexible, and it is possible to build complex tasks that can be a pipeline of many different tasks put together. Okay, so yeah, now we get at the end the same result as before. Okay, so that's the goal was to show you that it's very easy to run experiments from the command line. The only thing that we need to do is specify what are the tasks, and then running this moa.doTask, we perform this operation. Finally, imagine that we want to do this periodic health auto evaluation as before. So again, we are going to put this. We're going to use this moa.doTask, and then we are going to set what's the evaluation with the parameters, what's the classifier, the stream, and the parameters, how many instances. So we have this, we put on the command line, and then we plot them. Okay, and then in this case we are saying that the results of these are going to be stored in this ds result.csv file. So we are going to have the results over there. So this is very convenient in the sense that usually if you want after that to process the results and you want to create plots or this, you can then use this, output the results of this task to create the plots. Okay, so yeah, now this is, we are using a huge number of instances, maybe 10 million instances. So yeah, this is why it's taking so much. Okay, so yeah, this is how to use the command line. So now, yeah, we have these following two exercises. So the first one is repeat the experiments that we have been doing before, but now using the command line. Okay, so this is the first, and then the second is continue the comparison that we have been doing before, but now adding these ensemble methods that are these OSAVAC, this online bagging with 10 hovering trees, the OSAVAC Adwin that we have seen before with 10 hovering trees, and this leveraging bagging with 10 hovering trees, and then see how this increases the performance of our method. Okay, so yeah, let me do the first one. So to repeat the experiments of exercises 1 and 2. So remember that what we have there basically is that we have this command line. Okay, this was evaluate, interleave, test, then and train 1 million instances, and we were sampling with 10,000 instances. So the thing that we need to do is that we'll need to copy here. We copy it to the clipboard, and now let me see. Yeah, so we need to write this Java CP moa.jar. We use this Java agent to compute the memory, and then we do this moa do task. Now we write what is the command line text that we have been using, and yeah, it's simple then as plotting, and then we'll have the same result. This is the CSV file with these learning evaluation instances, all of this data that we have here in this intermediate panel. Okay, so we have this information, so getting here. So as you see, it's very simple to run experiments or using the command line or using the graphical interface. So the results are going to be the same. So it's very easy to run in both systems. Okay, so yeah, so we can do this for all the experiments that we have been running before. And now, yeah, let's go to the interesting part. So how we can improve the performance of our classifier. So remember, we have seen, yeah, we have been, yeah, this is the performance of naive Bayes. So that's the performance of naive Bayes with this random radius Bayes function generator rift of a concept with a change of 0.001. So yeah, this is with the naive Bayes. If we look at the hovering tree, then the performance gets a bit higher. If we look at the performance, yeah, this is the hovering tree with a majority class. And then finally, if we do that with the OSAVAC Adwin, we see that the performance is getting much better. The interesting thing is that this back Adwin is it's an adaptive bagging, so this is why the performance is good in the sense that it's adapting. Okay, so if we look at this exercise, basically it's saying we have been using the interleave, test, then and train. Here they are asking us to use the sequential evaluation with a sliding window of 1,000 instances. Okay, so let's do this. So now we need to start a task with evaluate sequential. We are going to start with this OSAVAC, meta OSAVAC 10 Hofding trees. Now we are going to set up the stream. It's going to be this random radius-based function generator drift with 0.01. Okay, 1 million instances, frequency of 10,000. Okay, so now we are going to run this. Yeah, now we're going to try with OSA-back Adwin. Again, now we only need to change the classifier. All the rest is the same. And finally, the third one is this leveraging bagging with 10 Hofding trees. Okay, so now again we're going to set up this leveraging bagging. As you can see, we can run these three tasks in parallel, so we can run them at the same time. So we can see how this goes. So this is we see this is the accuracy of OSA-back. We have already 82%, and right now accuracy it's around 62. So this is frequential using a sliding window of 1,000 instances. So that means that the current output is the accuracy of the last 1,000 instances. It's not the accuracy from the beginning. So that was from the interleaf test and untrained. Okay, so in that case, it's useful to look at the mean, because the mean is going to give us the mean of all the values that we have seen. So in that case, we see that this OSA-back, that's without any change detector, this is getting this final accuracy of 62.10%. If we look at the OSA-back Adwin, we see that accuracy goes to 71.50%. So that's an advantage of being adaptive. And now we look at the leveraging bagging. We see that this is a method that takes more time, but also at the same time we see that the performance also is going to be much better. If we are looking right now, still we have 57%, but we already have this 82% of accuracy. So there is always this trade-off in data stream mining between accuracy and resources, because usually the method that uses more resources can be much more accurate. But sometimes in streaming we are in this real time setting where we really need to have very fast prediction. So then in that case it's always this trade-off between the resources that we are using and the accuracy that we are getting. So this is why in streaming we always need to give the evaluation measures of accuracy, but also time and memory. Because it's not only the most accurate method that we are interested, we are always interested in the method that is more accurate, but also fast, and that uses the less amount of memory possible. Okay, so let's see this one. So now we'll see this leveraging bagging. So at the end, we see that the accuracy is 84%. So if we compare with Adwin bagging, that was 71%, and the online bagging was only 62%. So the only thing is that we see that in terms of resources that we are using, so that could be time, but also we can look at memory. That is in that case it's RAM hours. That is a measure that combines time and memory. What we see is that leveraging bagging is really getting much better, but it's also using much more resources. So it's using a higher number of resources. Okay, great. So with this we finish these two exercises. So now maybe I'm going also to show you how to do regression. So in that case, in regression, what we want to do is to predict numeric values. So in classification we were predicting labels. So now we are going to look how to do regression that is predicting values. So in this case, we can use also a decision tree. In that case, it's going to be a classification tree. It's going to be a regression tree. There is this state-of-the-art method that is FIMTDD. That's a method that is a regression tree. that is based also on the housing bound. So the main differences basically is that instead of using information gain, it uses variance reduction, and that it uses the average of the classes at the leaves instead of the majority class. So only to show you an example, in Mo, in the graphical interface is very simple. We only need to go to the regression tab, and then we need to configure the task. So let's choose evaluate frequential regression. So here again, we need to decide what is the learner. We choose this trees FIMTDD. That's the regression tree. Now we'll need to choose one stream. So let's choose one file. So we are going to get one file that is this. Let me find it, a census dataset, census.arf file. Class index should be 1 because it's the first attribute that we want to predict. And now, again, we put the instance limit. We say that we want to sample every 10,000 instances, and now we can start to run the experiment. So we see that this is similar to classification, but now the measures are going to be different. So instead of looking at accuracy, now here we are looking at mean absolute error or a root mean square error, and these are the things that are plotted down here, so that we can see how this, and again, this is a very big data set, and then we see how this is done, and how this performs over time. So in that case, this is the error. So here it started with a high error, and now with time, the region tree is growing, and it's becoming much more accurate. Okay, again, so in that case, this is going to be a large data set, so it's going to take some time. There are other methods that we can use that are much faster, as the perceptron. But in this case, it was only to show you how regression is easy to run as classification. The only thing that basically we need to change is data sets, and we need to change the classifiers that we are using. Should be regressors instead of classifiers. Okay, so I think that with this, we finish these exercises. So now, let's continue with the discussion of these methods with Bernhard.
Back to some explanations. So, just seen some regression examples. Now we're going to look at what algorithms there are in MOA. How do they work? It's going to be very brief, because unfortunately, regression seems to be a slightly neglected area. So if you look at MOA, you'll find that there's probably less than 10 different algorithms currently, whereas you saw this long list for classification. Of course, you can always use something like a simple linear method, stochastic gradient descent with various types of losses, or what is kind of the state of the art for a lot of regression problems in streams, is FIMTDD, which is a fast incremental model tree with drift detection. So it's a decision tree, but it's not just splitting and then predicting the average at every leaf. There's a linear model at every leaf of some size. And it has built-in methods for detecting drift and then modifying the tree appropriately. But other than that, it's kind of very standard, kind of use the template for a Höfting tree, and you just adapt all the things that are different, because we now have a numeric target instead of a class. So instead of info gain, we need to minimize some numeric measure. Here in FIMTD, they use the standard deviation that's minimized. For numeric attributes, they have made this decision to use the full binary tree, but prune parts of that if it takes too much memory. So it's actually quite a complex part of that algorithm, and wouldn't be surprised if there were still a few bugs in there, but I don't know. In the model, in the leaves, you have linear models that are trained by stochastic gradient descent, which is nice, straightforward, it's incremental, and also scales well. So even if you have a lot of attributes, it's still linear. It's not cubic or something like that. Drift detection does not use Edwin. It uses another test called Page-Hinckley, but it's kind of similar. And if they think there's drift, they start growing an alternative branch, and then have yet another measure, that's called the Q statistics, to decide whether the new branch, after I don't know how many examples, really is better than the old one and should replace it, or not. And then we remove one of the two options. And again, there's also an option tree-based variant of this, and it's really state of the art. Not a simple but effective method is nearest neighbor. And I've already talked about how it's very easy to implement nearest neighbor. And of course, it can be a bit more smart in terms of also having an adaptive window size. If things are stable, grow a larger window. If they change, have a smaller window, but be careful to not use too much memory. And yeah, so you can, for instance, use Edwin to explicitly adapt the window size. You may not want to throw away all the old data. You might just keep some of the old data around, just in case. And of course, if this is not giving you the performance that you want, you can use it inside some ensemble method. And it turns out that leverage bagging actually functions pretty well for that. Okay, so that was basically all I have to say about regression. Now we need to move on to another area. And just to, from now on, all the things that I'm going to talk about will be very brief and high level, so that we cover quite a number of different things in the little remaining time. So I think we probably have a bit more than an hour left. And we have a lot of stuff that, yeah, it's exactly an hour and 7 minutes. So clustering. Clustering is an area where in stream mining, really almost every single clustering algorithm is just an adaptation of something that was used in batch learning before. So this is just a reminder for k-means. You probably all know how that works. It's very simple. You somehow choose centers, you assign points to the closest center, you recompute the center from the points, and you iterate that until you converge, or until some other stopping criterion like maximum number of iterations has been hit. Now, looking at streaming, there's a very simple way of having something which is online, where you collect a few data points into initial setup, and from then on, you have some initial cluster centers. Whenever a new example comes in, you compute the closest center and just add that example to that center, which also means that the center moves a little bit into the direction of the new example. Of course, over time, the centers will be very heavy and not move much anymore. And especially if you have change, there's a new center developing somewhere, this can't model that well, because it will take for a long time for an old center to move into the new high density area. So it's a slightly smarter setup. And there's an example for one of those standard ways of turning batch into incremental. In this case, it's batch incremental. What we can do is we can collect data for a batch and then cluster that. And then use the clusters from the current batch, the clusters from the previous batch, and maybe try to find how they match up. Which one is the closest, so that in a way we might see how cluster centers move around in space, or old ones disappear and new ones appear in new areas. Or we can even be more sophisticated and try to, with the close ones, kind of have a weighted sum of the old and the new, and so have more information for maybe a better global clustering. And it brings me to this fundamental data structure for online clustering. Because if you look at what k-means does, how do you compute the center? The center is the average of the points assigned to the center. Now, if we keep as a data structure the sums of the attribute values of the examples that were assigned to the center, then we can basically update centers incrementally and with every single example. Now, generally what you also want, sum of squares, because that allows you to define something like a radius. Because turns out it's very important to not add a point to something that's very far away, even though it may be its closest cluster. Because if it's very far away, it's probably an outlier or the start of a new cluster. So you might want to do something different, not just adding it to an existing cluster and thereby maybe polluting that cluster by shifting it into the wrong direction. Nice thing is that, for example, this update is O of 1 is constant. Of course, it's linear in the number of attributes, but that's a given. And nice thing is also because it's completely additive, we can also merge clusters by just computing the sums. And again, splitting is also an interesting option. If data from a cluster drifts apart, at some stage you might want to split it into two clusters. This is also where the standard deviation is useful, because you can see like in which direction the cluster is more elongated, and then maybe you split in that direction in an estimated way. It's not going to be precise. And with those sums, as I said before, over time they will be pretty big, and every new point won't have much influence. So one way of dealing with that is again using forgetting factors, so that you discount the old sums a little bit, so that new points have more influence. Now, what we're going to look at very briefly are a couple of reasonably sophisticated current algorithms that usually work with these microclusters. So, first one, Burge, is actually an instance of the two-level scheme. As two levels, where the first one is fully incremental, and the first one builds a B-tree-like structure of microclusters with a user-specified maximum radius. And then at level 2, what they do is very simple. Whenever they want to have a proper clustering, and there can be every so many examples, so demand-driven when you need one, you just use the microclusters from the first level and run standard weighted k-means with those microclusters. Works reasonably well. Now there's a variant that's called Pico that is a bit smaller, that uses ideas, so-called core sets. So a core set is a very general idea. It's usually a useful approximation of something that helps you achieve your task with a lot less memory and computation time. So what they do that here, they actually get one of the fastest and well-performing current clustering algorithms. Then an attempt to be more precise and more explicit about change over time is a class stream, where you have explicit time information associated with microclusters. And then, for instance, if you find that some microclusters become too large, then you might delete an old one, or you might merge two old ones if you need space for new ones, stuff like that. So time information can be very handy for this. Now, all of these algorithms that are kind of in the k-means family have this issue that they rely on a distance or similarity function, and that first of all, if you have many features, then you have this curse of dimensionality, but also they assume nicely spherically shaped clusters. Now in practice, clusters sometimes are not as nicely shaped. They might be weird structures. Now luckily, an arbitrary weird structure can usually be approximated with a number of microclusters that are spherical. But because it's not very satisfying, and you need a lot of microclusters, of course, people have looked at alternatives, and the kind of best known alternatives are usually density-based. And so basically the idea is you can get an estimate of the density in the area by computing neighborhoods where 2 points are connected if they're close to each other, or if you have a bridge of closely connected points from A to B. So they can even be far away in this weird shape, but if there's enough points in between, they kind of form this nice cluster. There's a batch algorithm that won the authors a prize at KDT a few years ago, dbScan, which tries to do this for batch setting. Now, of course, what we do in streaming, we take that and try to adapt it. And one of those attempts is the so-called dense stream algorithm, the density-based streaming clustering. Again, two-level approach using microclusters, and then basically implementing DB scan on the microclusters that you've collected. I think I skipped those. This is another interesting algorithm that's reasonably recent, where they actually tried to be serious about real-time performance. So they have a hierarchical structure, a tree for the microclusters, but every tree node actually has this distribution information that we keep, and then additional space for new data. And so the idea is that you have a new data point, you process that, you add that, and you go down. But now here we're stuck because there's a new data point coming in that we want to process. So we just keep the old information in this overflow space here. And next time we get down here, we might actually push the whole lot down, the new data and the old one. And that works pretty well, but it takes more space, of course. But it really can adapt to data that comes in at irregular intervals. So if you have very fast points, then you might see a lot of interrupts, but then if there's a little bit of a pause, then the next point that comes in might actually help you clean up the tree and push all the data where it should go. And I think that's the final one that I mentioned. Stream KM++, again, is a reasonably straightforward variant of K-means++. K-means++ is kind of smart in the way it initializes its cluster centers. Because it turns out that in standard clustering, choosing the initial centers is essential. If you choose them well, you're almost done. If you choose them badly, it may take a lot of iterations to converge, and you may converge to a suboptimal solution, because unfortunately it's a heuristic algorithm. There's no global minimum. You're not guaranteed to find a global minimum. In practice, KM++ works pretty well, and the stream version is, again, very similar to what you need to do. It's two-level, an incremental first level, and an offline phase, where in the incremental level, like with Pico, you have core sets that you collect, and then you use K-means++ at the second level in the offline approach over all the core sets. So just basically more sophisticated microclusters. Now, there's a big problem in clustering, and that may be one explanation why it's being used a lot in practice, but it's not being researched much. It's hard to publish evaluations. Because if you look at classification or regression, small number of measures that we all agree on, like accuracy or area under the curve or position recall, F1. There's a few, but there's not too many. Here, there's a lot. So this is not a complete list, but it's about 20 so-called internal and external ones. Where internal basically means you don't have additional information, but you somehow try to judge the quality of a clustering. And external means that you have some labels for your data, and you compare how well the cluster structure actually corresponds to the labeling. I said way too many. So it's a bit of a hindrance. Now, we should have a cluster demo. So there's no exercise, it's just going to be a quick demo to show you what's in MOA.
Great, so let's see a demo of the clustering. So let's see how these things goes in MOA. So there is a tab specific for clustering. So this is work that was made by the group of Thomas Siedel at University of Aachen. So the idea is that we are going to choose between two algorithms, and then we are going to compare them in a graphical way where we are going to see the evolution of the two clustering. So let me only just remember how this is done in Weka, in the batch setting. So in the batch setting, we have the data set. So imagine still we have the same data set, this electricity data set, and then we want to apply k-means. So basically, we are going to decide how many clusters we are going to have. So imagine that we decide we want to have 4 clusters. So we decide this, and we run the method. And then at the end, the result is that we have the coordinates of the 4 clusters that we have decided. So that's the result. There's nothing, it's static, there is no evolution on this. What happens in MOA? So what happens in streaming? So in streaming, the data is going to be evolving, and we need to be able to have a clustering for each time, for each instance of time. So let's see again. So we're going to choose this stream that's going to be generated from this radio-based function objects, and we'll see we should choose two algorithms to compare. So let's choose, for example, one of the ones that we have been introduced right now, for example, class 3, and we compare this with class stream using k-means. Then we need to choose what's the evaluation measures. So yeah, in that case, we use this purity and precision, recall. And now the interesting thing is how we should look at this on real time. So the idea is that we start our evaluation. So let's see what's happening now. So here are the two methods. So let's start with the beginning. So these are the points that we have, okay? So these are the points. So we need to do this cluster. As you can see, this is something that is evolving over time, okay? So these clusters are evolving and are moving, so we need to be able to do the clusters over time. So what's the ground truth? So what are the clusters that we want to get? So the clusters that we want to get are these ones. What are the clusters that we are getting? So these are the clusters that we are getting, okay? So if we look at this, so these are the clusters that we're getting. This is class 3, and this is class stream. So we see how this evolves over time. So we see how these clusters are merging, they are merging, are splitting. So there are many different things that all of these clusters are events that are happening on real time. You will see that we have the ground truth. This is what we want to get, but also we have these micro clusters. So this is what we have seen, that the majority of these methods of stream clustering, they have this intermediate step that is to have these micro clusters. Computing these micro clusters is really fast, so we can compute this online. We don't need to do many iterations, so we do it very fast. And then at the end, we have this offline phase, that is, once we have these microclusters, we get the clusters, and then we use the standard batch clusters as k-means or dbscan. So that's the how this works. So this, imagine that the stream, we really have millions of points, but microclusters, we can keep only 100 points. And this, with 100 microclusters, we can do a very fast k-means or dbscan, so we can get our clusters on real time and see how they evolve. You can see also that here, it's like in the classification. Remember, we have the measures. So here we see how also these measures, they evolve over time, and we see how the two methods, the two clustering methods, they evolve over time. Okay, so let's continue a little bit more. So we see how this goes. So we see how the measures, they evolve. You see this is really, these clusters are moving very fast. So this is also a parameter that we can change. So there is no need to have only one. And yeah, the nice thing is that we can decide how many instances we want to have. So we can run this really continuously. And again, the important thing here is that we see how all of these measures, they evolve over time, and how our clusterings that we are getting, these are changing over time. So these are the clusters. You see that the clusters obtained by the two methods are really different, and that this is something that it's evolving over time. As I said, the idea then is that we can change. So maybe let's run another experiment. So we can change what's the method that we are using. Imagine that instead of class 3, we want to use dense stream. Okay, remember that dense stream is this method that is like the version of streaming of dbscan. So here what we are going to do is that we are going to be density based. So clusters are not going to be spherical as in k-means or class stream. The clusters are going to be the ones that are connected. So the ones that are really points that from one point inside the cluster, you can reach all the points from this cluster. So let's see this example. So let's start. So here we see the difference. So the difference here is that these clusters, in dense stream are connected by density. It's not connected. They are not created by this class stream that is connected by this sphere. So each cluster is a sphere. So here each cluster is going to be points connected, and we see how this continues. So how this works. But again, this dense stream method works also with using these microclusters. Okay, if we look at these microclusters, so these microclusters are computed really, really fast. This is done online, and then after that we compute the real clusters using this offline methodology. Okay, so yeah, I think that's all for this clustering demo. So the only message here is that yeah, we have already this method implemented of clustering, but then it's very easy to add more methods and then run experiments and compare. And then, as you see, there are many different measures that we can use, and you can see how these measures, they evolve over time, and we see them here. We can see the results. Okay, so yeah, now I'll continue with other discussions.
Okay, everybody. I need to go back to full screen mode, of course. Here we go. So that was our cluster demo. Now, it's the last bit of slides, and I'll, in a very brief and quick way, we'll try to cover a few more different little areas. And I suppose we will have enough time for a little programming exercise as well after that. So, because so far, what we've shown you is how to use the GUI and how you use more from the command line, but we haven't shown you how you can actually use more classes in your own programs, how you can write Java code to set up experiments, how you can implement your own new classifiers, stuff like that. But before we do that, I just want to quickly cover a few more interesting angles in stream mining. First, I'm going to talk like 1 or 2 slides about pattern mining, then pre-processing, and then a number of other open issues. And unfortunately, there's even more than that, but we won't have time for that today. So this should look familiar to everyone who's done an undergrad course. You have different types of patterns. You have the frequent item sets, you have the generators, you have the closed frequent item sets, you have the maximum frequent item sets. And there's certain properties, like there's a lot of frequent item sets, there's a lot less maximal ones. Generators are usually very small, they don't have many items, stuff like that is useful. And again, most methods, with some exceptions, there was a paper yesterday that actually talked about a batch-free pattern miner at this conference, but most methods use this batch incremental setup, and here's just a generic approach to that. So basically, you have 2 levels. You have a batch, you collect the data, then you process the batch, and then you have some kind of set of patterns, and you may merge it with old ones, or you may replace the old ones completely by that. Then you go on for the next batch. And of course, a lot of detail, a lot of sophistication that you can put into what exactly do you do with each batch and how do you merge or somehow combine the new with the old patterns. Again, this first level needs to be fast and incremental. And so an obvious solution is that you have some sketches to count frequencies, like this is space-saving algorithm, which we couldn't cover, unfortunately, but you'll find it like various books or Wikipedia, or I will also make the full set of slides available that I used in this winter school, where this is explained in a little bit more detail. Issue with that is that you need memory, because you need to have an idea of what patterns you're actually looking for, and then for every pattern you need a count or some counting data structure. And in the simple setup, you can count and add, but you can't forget or subtract. This is inherent in some of those, the way some of those algorithms work. There's a more sophisticated algorithm called the moment algorithm, which actually only looks at closed item sets and keeps them exactly over a sliding window. And it's actually quite a complex algorithm. It has 4 types of nodes in a tree structure and very complex update procedures. But they can prove that this gives you exactly the same result in terms of the patterns that have been extracted that you would have gotten if you had just this batch and applied a regular learner. Yesterday, at the prize giving, someone mentioned FB tree as an alternative to a priori. FB trees are kind of really cool and useful, and so it's no surprise that there's an algorithm that uses FB trees in a streaming setting, and it's called FB stream, where basically, instead of having one tree, you add more information to every node so that they keep the time information as well, and not just the counts for your batch database. Now, if you are happy with errors, especially if they're one-sided, and so, for instance, Bloom filters are an example for that. They can be very useful, even though you know that they will get it wrong at times, but they will only get it wrong in specific ways. Something kind of similar is the so-called ink-miner algorithm that is much more approximate or crude and has false negatives, so it will declare some patterns to be frequent, even though they're not, but it is a lot faster. So for especially large or fast streams, this is probably one of the algorithms that you want to go to. I'm not too sure about the algorithm that was presented yesterday in terms of efficiency. I would have to read that and talk to the authors. That might also be now an interesting option. Now another thing, in applications it's very important to do the right pre-processing for machine learning in general. Some people claim that's basically 80% of the work, and after that, if you have a good representation, there's not much that you need to do with machine learning, and almost every reasonably sophisticated algorithm will give you good results. Of course, there's the deep learning people who hope that they will be able to not have to do the pre-processing, so that the machine will do all the 100%. But in streaming, if you look at it, again, like regression and some other areas a bit neglected, there has been quite a bit of work on PCA as a pre-processing method, online versions of PCA, which are actually quite sophisticated. But as far as I know, almost all of them do not deal with change. But it's not necessarily a big problem, because again, you could use some two-level setup, where you have the online PCA at the first level, and then have a change detector. And when you think something is badly changed, you might restart the first level or something like that. Now, there's one exception where we have good methods, which is discretization. There's a standard algorithm called addition incremental discretization, which basically everyone uses. And originally there was only additive, couldn't forget. But now we have versions where you can also forget. So basically you can use the sliding window, for instance. Now, I have a little tricky question for you. So, assume someone gives birth to twins, and twins, they don't get out of the womb at the same time. They have to do it one after the other. So let's assume that it's about half an hour in between the two events. And let's assume that the birth certificate records the time. Now, looking at the birth certificate, the second one seems to be older than the first one. Is that possible? And if you claim it's possible, then you need to give me an explanation of how this is possible. So twins. And for some funny reason, we claim that the second born, legally speaking, is the firstborn. And that may have consequences for who takes over as the king of Scotland, or something like that.
Maybe it got processed first by the certificate.
Yeah, okay. Some simple error. Okay. Yeah, that could well be. It will probably happen at times. Hopefully not often. There's actually two possible explanations. One is if you think about daylight saving time. So on the time point where we switch back, at the first one is born, say, at 1:55. Two, we switch back to 1, and the second one is now born at 1:25. And it's half an hour earlier according to the legal papers. The other, so this could happen, I think. But there's another explanation that it's much more unlikely. When I asked some student that, the explanation was, the birth happens on a plane and you cross time zones going from west to east. But I'm not sure how they would record the time of birth on a plane anyway. So I quite liked it, I have to say. I think kind of the message behind that is, unfortunately, dealing with time is really, really tricky. So the simple answer is to always use UTC, but even that is not good enough. I don't have the links there, but there's a couple of really interesting YouTube videos that go into all the details of things that can go wrong, even with UTC, because time is such a mess. We have daylight saving time, we have different time zones. We have countries that have switched time zones. Like Samoa at some stage decided that they want to be closer time-wise to New Zealand and Australia. And so now they're one of the first countries to see this new day, where they used to be the last one. And sometimes the time zones are not 1 hour after the other, it's like 15 minutes or 45 minutes. Or you have a country like China where there's one time zone in the whole country, which again has interesting consequences. Now, another thing about times is this thing that really literally happened to me, honestly. It was when I'm moving from Europe to New Zealand in the year 2000, at the end of February, and we had a stopover in Singapore, and so we booked a hotel, and the booking, back then it was all on paper, said we're going to check in on the 27th, and we're going to check out on the 2nd of March, but it also said it's 3 nights in total. Now, this is a bit of an issue, because the way leap years work, 2000 is a leap year. So, every 4th is one, then every 100 is not, but every 400 again is one. And I had a long discussion at the check-in with the person there, until finally I could convince them, by looking at the amount that we have paid, that we probably had paid for 4 nights, and that we should be allowed to stay for 4 nights from 27th to the 2nd. Okay, so unfortunately, there's not much in terms of pre-processing. To be honest, there's a little bit now happening. I'm in the lucky position to work together with some PhD students from Brazil. So I'm not the official supervisor, but he has visited Waikato and we do research together. And he started to look into feature selection for streaming, which is very interesting, and there's some interesting things to be done there. Now what I wanted to discuss here is what I already mentioned when we started today, is feedback, or in other words, the ground truth, the labels. Where do they actually come from? And I already said there's 2 scenarios. One that's the easy one, where there's just a delay. Hopefully not a long delay. If you want to predict something for next year, you have to wait for a long time. But often what you want to predict is short term, and then it's fine. But then there's all these other cases where it's expensive or impossible to get ground truth for everything. So for instance, an example that a long time ago I've been looking at with a company in Germany, they looked at gearboxes. And they wanted to predict by basically listening to the sound that the gearbox makes, if the gearbox is about to fail or not. Now, you can't get ground truth for everything, because you would have to monitor everything for as long until it finally fails. I mean, these days maybe, because you could think of if the gearbox is in a car and the gearbox fails, the car might actually send some message home to the car manufacturer that that specific gearbox has now failed. So these days that might actually be an example that works. But if you want to do destructive testing, like the lifetime of the light bulb up there, you can't do that with every single light bulb, because then you won't sell anything, you won't make money. Or the example with house prices I mentioned earlier, not every house is being sold every month. It's only a small number of houses that are being sold. And so for lots of those predictions, maybe in a few years we might get an update when the house is finally sold, but sometimes houses are not sold for decades. So one idea here is, in these cases where it's expensive, to use ideas from active learning, so that you somehow identify useful examples where you want to spend your resources, like Amazon Turk or whatever it is, some expensive method of investigating, basically. Again, there's issues with streaming that you need to be careful with, and as usual, randomization is probably one of the answers. So for instance, a very popular method for active learning in batch setting is uncertainty sampling, where you mainly look at examples around the decision boundary. And now if the decision boundary changes in a smooth way, because you actually sample there, you will notice that and you can adapt. But if something changes far away from the decision boundary, like suddenly we have a new class there appearing, we will never notice because we'll never ask for a label that is so far away from the decision boundary because we had been very confident that this is still a green point. So it pays to combine this uncertainty sampling with just a couple of randomly labeled points, or randomly chosen points for labeling. So every now and then you choose one of the points that are really certain, and then maybe you get a surprise. Maybe you've chosen a point and you're being told, it's a new third class, the black one. Now usually also you want to focus you want to make the most of your limited resources. So you want to focus in interesting areas, and one claim is that interesting areas are the high density or the cluster structure areas. So for instance, even with uncertainty sampling, in this case, this point here is totally uncertain, but there's not much point in asking for that label because whatever that label is, it will have some influence out there, but there's no data. Much more interesting to ask for something which is here in the core. So say if you choose that point for labeling here, and that turns out to be green, then this linear decision boundary completely changes anyway, and this guy is now completely uninteresting. And there's a guy in Germany, Georg Krempel, who spent a number of years on researching that. And he built a couple of systems, one more sophisticated than the other, where he uses some interesting ways to estimate densities, usually with some RBF kernel-based idea, and then trying to find the points that give you the maximum or the expected maximum information for your future labeling. There's very interesting stuff that is done there. So this is just one of the papers, and there's a number of others. We're getting close to the end. In our examples, with a few exceptions, we've been mainly using generators. The reason for that is, first of all, they're convenient because you can exactly generate what you want to investigate. So, for instance, if you want to investigate change detection, in your generated data, you know exactly where the change point is. And so you can precisely measure the detection delay, for instance, or the false and negative positive rates and the true alarms. So they're useful. But also the other reason, the more practical reason is, unless you work together with a company, most of the interesting data streams are the property of some company. There's a number of exceptions, like Twitter gives you at least a 1% sample. So a lot of people collect tweets just because it's easy. And it can be interesting, depending on what you look for. And then there's the other, I didn't mention there, of course sometimes you can scrape web pages in an online, ongoing fashion. But sometimes that may be borderline in terms of the terms of services of those web pages, and they might take you to court for doing things, or basically asking you to cease and desist in very clear terms. But the other question is actually whether we really want pre-canned data sets like a UCI archive, or whether it would be more appropriate in this area just to have a listing of sources, like the rain radar that I mentioned. That one was New Zealand, but as far as I know, at least in the OECD area, every country, and often it's broken down to much smaller levels, you get rain radar. So if you want to work with rain radar, you can quite straightforwardly scrape that, and often they have, like in New Zealand, they do 7.5 minutes now. So every 7.5 minutes you get a new rain radar image. And predicting an hour in advance works pretty well. More than 1 hour, it gets kind of more and more dodgy. But 1 hour is not too bad. Yeah. It's a lot more. I mentioned feature selection already, then there's distribution. Remember, today I said we're going to look at the first system of the list, which is MOA, which is actually multi-threaded, but only on one machine. You saw the multi-threading actually when I was running like 3 or 4 experiments in parallel, which is nice to have. But it's not distributed. You can't easily use it across a cluster. Some MOA can do that, because some MOA uses some underlying infrastructure. There's various options. There's Storm, there's S3, there's Flink, Apache Flink, and not sure what else. There's a number of options. Now, another interesting research topic is seasonality or recurring concepts. And there has been a little bit of work, but time series people have done a lot more work there. Then true real-time behavior. Most things that we do here are kind of artificial. So we have one example after the other being generated, but we don't have explicitly specified time gaps between examples. So we basically count examples, we don't have time spans. There was this clustering algorithm that I mentioned that can actually do real time pretty well. And I mentioned the Lambda architecture, which is one idea that tries to kind of combine the best of both worlds. So it doesn't have to be solely streaming or solely batch. Probably the kind of best solution is somewhere in the middle. And maybe it's the Lambda architecture or something else that hasn't been developed yet. And of course, with the popularity, if not to say hype, but also the success for certain areas, the impressive success of deep learning, it is an interesting question whether we could use deep learning in some way for streams. And training from scratch is probably out of the question. But some people have looked into interesting things like using pre-trained models and then downsampling your data and averaging over various downsampled pre-trained predictions, stuff like that. So I wouldn't be surprised if there was a number of interesting publications in the next 1 or 2 years coming out in the area. And before I go to the programming tutorial, because we have a little bit of time left, I just want to show you this last slide. There's a summary for today. If you forget everything that you heard, the one thing that you should keep in mind is this oversimplified definition of stream mining, which is basically it's online learning without an IID assumption of your data source. And I hope that you agree with me that there's a lot of stuff that hasn't been investigated yet, lots of missing bits, which means there's good opportunity for research and development. And so this is a half full glass for me, but you may not agree with me. Thank you. And the remaining time will now be spent in a little programming tutorial so that you see a little bit of the API and how you can use that.
So yeah, we'll finish this tutorial with programming API tutorial. So in the website you will find that there are the link to 2 tutorials. One is the tutorial on clustering. If you are more interested in looking at clustering, you can see here with more detail how to run clustering experiments. And then we have this tutorial on programming using the API. So yeah, this is what we are going to look at now. So the idea is that basically we have these objects that basically are going to be the classifier and the stream, and we are going to be able to combine them to. In this case, we are going to run a very simple example that is we are going to run a frequential evaluation, okay, and we are going to do that using directly the classifier and the stream. Of course, in Moa there are other objects as evaluators and this, but in this case we are going to go for very simple. So let's see how we can use a classifier and how we can use a stream and how we can use this classifier first to update the model and then to do predictions. Okay, so yeah, this is the example of the Java code. Let's say that in this case what we are going to do is that we are going to do this evaluation. So first we need to define our classifier and our stream. Okay, in that case we want to predict 10,000 instances. So first we're going to build our classifier. So we are going to, in this case it's a housing tree. Okay, so first we are going to have a classifier object. Okay, this is the Java interface. And then we are going to create this new housing tree object. Okay, so with this we have the learner. Now we'll have the stream. In that case we are going to get data from this random radius-based function generator. So we create this stream object, and then we call this prepare for use method. So we will be able to use this stream. Once we have this, we need to tell the learner what is going to be the structure of the instances of the stream. So we call this method that is called setModelContext with the stream get header. So we are telling the learner how the instances, the structure of the instances. And finally, we also prepare the learner to be used. Okay, so yeah, this is the initialization step. After that, now what we are going to do is that we are going to feed the classifier to train and to test. So in that case, yeah, we can do that until the stream has no more instances. So this could be, imagine that we are reading data from a data set. So yeah, we are going to read on, we're going only to use the instances that are in the data set. Or if they come from an artificial data set, this is going to be a specific number of instances that we are going to use to do that. Okay, so we have this loop. That means that for each instance in the stream, we are going to do, first we get the instance. So this is used doing this stream.next instance. So this is the method where we get the new instance. And then if so we are going to be testing, what we are going to do is that if the learner correctly classifies this instance, we are going to add 1 to this counter. This is the counter that we are going to use at the end to output the accuracy. Okay, so we need only these two counts. One is the number of samples that are correct, and the other is the number of samples. And then once we run this, at the end we are going to output the accuracy as the division between the number of samples correct divided by the number of samples. And then we are going at the end to print the accuracy of this. Okay. The other thing, so with this we are only using the prediction if it correctly classifies, and then we need to train our classifier as we are in this frequential evaluation or interleave, test, and untrain. So first we test and then we train. And to train, we use this method that is called train on instance. Okay, so this is how we do that. Okay, so that's the idea of the Java code. So maybe, I can show you this in a real a small program. So imagine that we have this experiment class, and then we have we are going to run an experiment. We are going to say how many instances and if we are going to test or not. So so we see first we create the learner, then we create the stream. Now we prepare for use stream and learner, and then we start this this loop that for each instance in the stream, we are going to, if we are testing, we are going to see if it correctly classifies or not. And then at the end, we are going to do the training. And finally, we are going to output the accuracy that we get. Okay, so this is a very simple class. This is a main method that calls this experiment, and then is running this, has this run method, and so it's running this experiment, in that case, plotting this. So it's really, really simple. So just if we want also to do that from the command line, we have this experiment.java. We can see this. This is the file. So we only need to compile the code using a Java-C compiler. We compile it. Once we run it, so we only need to have a moa.jar in our class path, and then we can run it, and then we are going to get the results. In that case, this 1 million instances processed with 91.04% of accuracy. Okay, so you see this is really, really simple. Okay, so this is how to use the Java API, but maybe then what could be more interesting is to create a new classifier or create a new learner. So how we should do that? It's very simple. So basically we need only to write 3 methods. One is to initialize the classifier, one is to do the prediction, and the other is to update the model. Okay, so these are the 3 methods that we need to do. So the first one is called reset learning, and this is the thing that we need to do. So this is, for example, in this tutorial, this is the code for a decision stem. So it means a decision tree of one level, of only one root node. So here, for example, to do this reset learning implementation, so we only need to specify what are the objects that we're going to use. So we create them. Then the next step is train. Okay, so it's this train on instance implementation. So here is where we specify how we train, how we update our model. And finally, the prediction that is going to be using this get votes for instance. Okay, so this is the output. So we get an instance that we want to predict, and then using our model, we are going to output, in that case, it's an array of doubles. So this is going to be a prediction. And then for each one of these arrays is going to contain a probability value for each one of the classes that we have. Okay, so as you see, it's really, really very simple. So we only need to write our classifier, we write these methods, and then we put that inside the Java class path, and it's going to appear also in the graphical interface. So we really don't need to do complicated things. It's very easy to use, and it's very easy to extend. And then I think this is also one of the advantages of the open source software, is that it's very easy then to compare with other methods and run experiments. And then I think it's for me it's very important that the community, when the researchers they write papers, they also give the source code, because then it's going to be much easier for other researchers to replicate the experiments, and also specifically with the parameters that sometimes are really, really difficult to do. Okay, so I think that's that's all for the programming. For the programming tutorial. So it's as you see, we have this tutorial. If you are interested, you can look at the details of this. You will find how to use the API and how to build new classifiers using this. And I think that with this, I think this is all that we wanted to present today. So I think now we will be happy to answer questions or discuss everything that you would like to talk about. So thank you very much.